Surprise when I start. We're going to review today over what we need to know, what you need to know for the exam. So this will be covering primarily chapter 2, but we can't forget what we learned in chapter 1. So what we've learned so far is that quantum mechanics, we're looking at the wave nature of materials. And generally that's going to be dealing with small things. The Schrodinger equation, super important. What's the point of that Schrodinger equation? Find the wave function. And specifically, it gives us the wave functions for the energy states. We have to normalize that wave function. For the wave function to be normalizable, we had certain things that were required, like the wave function can't go to infinity at any location, and it has to approach zero as you approach plus and minus infinity. So we had some rules there for it to be normalizable. Our solutions had to be orthogonal to each other. Orthogonal in three-dimensional space, that would be, mutually perpendicular. But we're talking about multidimensionality. For instance, we did the particle in the box, which had an infinite number of solutions. And we have to kind of separate ourselves from the three-dimensional space at this point, because how could we have an infinite number of perpendicular directions? But that is actually what it means for them to be orthogonal. So we had our orthonormal condition that said that if we take a steady state solution, it has to be normalized, psi star psi integrated over all space is 1. And if we have two different solutions, like psi 1 and psi 2, if we do the equivalent of a dot product, which is integral of psi star 1, psi star 2, that's the equivalent of a dot product. And so that's going to be 0 if n is not equal to m. That's orthogonality. But if n is equal to m, it's equal to 1. And so we have that delta function that gives us the orthonormal relation. Now, Chad came in and he asked me today about completeness again. What does it mean for a function set to be complete? And what that means is that we have all of the possible directions, the unit vectors that exist. They all have to be orthogonal. And so if we're complete, if we have all of them, then any vector could be written as a linear combination of all of these solutions. And our example where we did that was where we had I gave the example the same as if you plucked a string. So we had our psi of x at time equals 0 looked like that. And then we found what the c sub n's were to fit that. And we only found the first, 4 or something like that. And you have to be able to do that for it to be complete. Now, as I told Chad, I don't know of any, I may be just not educated enough, but I don't know of any test to say that it's complete, other than you have to always be able to do that inner product for it to be complete. That is, you have to always be able to do, that's called an inner product, the dot product. Quantum mechanics is probabilistic. It's not deterministic. We can't say that if I drop the ball from this height, it's going to have this speed when it hits the ground anymore. We can say percentages about its speeds, but we can't say what the exact is going to be anymore. And that makes no sense, right? I mean, if I drop the ball, assuming there's no air resistance, I should be able to get it exact. And that's how Einstein felt, that he thought quantum mechanics, maybe we just don't understand things right. If we knew everything right, we should be able to determine it. But our understanding of quantum mechanics is, no, it's probabilistic. That nature, God does play dice with nature, to change the quote of Einstein. And so what do we get out of quantum mechanics? What's the point of studying quantum mechanics? The point is that if we have operators acting on our wave function, which I don't have written on here, they will give us observables. So it makes predictions of what values will be. That's the usefulness of quantum mechanics. So problems that we have tackled, things that we've done, particle in the box. How do you feel about the particle in the box problem? Better than the other ones. Good, good. Then we did the quantum harmonic oscillator. Two different ways. We did it with the ladder operators. As you can see, the ladder operators are there on your equation sheet. And then we did it the brute force method. You should know those two methods. Not that you're going to have to do it, but you should be able to describe them.
So like that homework problem that we had where we had to list the steps of the analytical way?
Yeah. Yes, like that.
Problem?
Yeah, like that.
The whole thing would be a problem? Or do you, like every single step might...
You should know what the steps are. Yes, okay. You should know all the steps. You don't have to do any of the steps.
Right.
But you should know all. Okay. Then we have the free particle. Now with the free particle, we didn't do very much, did we? We have things like group velocity and phase velocity. So make sure you know what those are. And with the free particle, it didn't have quantized energy. And we didn't have a normalizable solution. I did, by the way, we didn't talk about the flux. So I went ahead and removed problem 1 from the grading on the homework. I saw you already turned it in, so I sorry that you spent time on that. Well, I'm not super sorry because you probably learned something, but it's a bunch of oh, you didn't do it? Oh, okay, then no loss.
That last problem took me so long. I think it counts for 2 problems.
Okay, so I'm extra glad I made that decision now. Okay, delta function potential well. We had 2 variations, the one that we did in class and the one that was on the homework, which I am going to spend the rest of the class period in a few moments going over. And so with the delta function potential well, we found only one solution for the bound case. What made it a bound case? When the energy was below 0 in that case. And then we did particle in a finite potential well. That's the last problem we did. I think that's the last problem we did. Yeah.
So with that particle in a finite potential well, what we ended up with here was just equations in terms of z that we set equal to your like graphed and then found the intersection.
Right.
We never found like a specific quantization of energy, like, or it wasn't.
Okay.
Are we expected to find that?
You're right that I did not give the final state.
Yeah.
So let's just, looking, actually I have that, I can bring it up. After all, I think, I only have 3 more slides here. I'm just going to go to that and then I'll come back to this. So looking at the problem, okay, so where's that graph? Yes, this is the double well. Okay, so here's the graph. So with our definition of Z, we're able to find the values of intersections. So we're able to find the Z values that comes out. So there's our quantization. So we get, and I believe I listed here the values for Z, I hope. No, I didn't. Okay, so from analyzing the graph, or like I said, using a spreadsheet, which is what I do, you actually get the values for Z. And then that Z is quantizing the energy, because going back to what Z is equal to this. And so if I find what the Z values are, then I can just solve this and say, well, Z squared over A squared is equal to 2m E plus V0 over h bar squared. Now I multiply both sides by h bar squared, dividing by m, so h bar squared z squared over 2ma squared is equal to E plus V0. And then finally, E is equal to V0, or excuse me, that's going to be a minus V0, so I'll put at the end. H bar squared Z squared over 2ma squared minus V0. And so you put in each of the Z's you have, so I'm going to have a Z sub n, that's supposed to be an n, to get an E sub n. And so you get each of your E values, each of your energy values, based on what the Z value was when you had the crossing here. So like I said, for this one here, for n equals 1, it's somewhere just in front of that dashed line. So it's somewhere here like 1.8-ish is the best I can read on this. To actually do it, like I said, I'd make a spreadsheet and I would zoom in, zoom in, zoom in to find exactly what it is. And so that's how you find what the energy levels are exactly. And so you can get, if you know what, right, the A matters here and the V0 matters. But if you have those two parameters, then you can get what the exact values are.
Okay, so in this example, there were 6 quantized energy states, and
yes.
Could there be more than 6 or fewer than 6?
Yes. It depends on, okay, so in our definitions here, I say yes. I'm pretty sure that the answer is if you have a deeper well, you're going to have more states. I haven't excuse me, I haven't gone through to double check this, but I'm pretty sure that with the deeper well, you're going to have more energy states available to you. I would have to go through and do it carefully to make sure on that.
But the way we do the math for any finite particle in a well is the same as what you did here.
Yes.
We changed the V0 and we changed the A.
The A, yeah. And the N.
Yeah.
And let me admit here, I hope I did my math right. Yeah. Last year my grandmother died. Okay. Going back to the review then. Did that get you what you wanted?
I think so. Yeah.
Actually I should come back here one more thing. The values for B equals minus F and B equals plus F, you then can normalize to get your full wave equation. You have the wave equation was go back one more. Here's the wave equations. Okay, so here was our solutions. And then once you've decided which state you're in, you can find the B and the F and the C and D from those and have the normalized solutions. And that's just more work. And I didn't push you to do the more work there. But that is how you end the problem, right?
So we only, in your example, you normalized and found the D constant, but you would have to find B, C, and F.
In my solution here, I don't think I did the normalization calculation, did I?
Yeah.
It's right at the top. Yeah, you're right. Okay, so I did. Okay, so I did normalize it. Hey, yay, good times. Yes, normalize it better, more than wrong one. Let's go back to the review and then we'll look at problem 4. And you can still, if you find something that needs to be redone as we go through problem 4, you obviously can still turn it in. Okay, so steps used in virtually every problem we've done. First, you need to identify the potential energy function, which usually is just going to be given to you. But sometimes, like if you're in real life, nobody gives you anything. Then use the time-independent Schrodinger equation to find the solution in each potential energy region. Now, this is the first time in our review I've mentioned the time-independent Schrodinger equation. If you look in the equation sheet, you'll notice I gave you a time-independent Schrodinger equation and I call it a spatially independent or something like that, Schrodinger equation, position-independent Schrodinger equation. The full Schrodinger equation depends on both time and position. And then we separated them, which only worked if we had a potential energy function that was not a function of time. But then by separating, we said, anytime we find our solution, our full solution is going to be the spatial solution that we find from the time-independent Schrodinger equation multiplied by e to the minus I e h bar t, whatever you get from solving this equation right here.
Do we have to do that?
Yes, you do. Right there's that is equal to that times that. And so you should be able to solve this equation, which it's only a one-stepper.
Oh, yeah. Okay.
So you need to remember the complete solution should have the time in it. But the time is always going to be the same thing. And so that's why we have separated ourselves. But on the test, I am specifically going to ask you that. I want to make sure that you remember there is time in these. It's just a simple part that we multiply in. Okay, so we found the solution for the time-independent Schrodinger equation for each region. Then we used boundary conditions. So make sure you know your boundary conditions. And my next slide actually is boundary conditions, so I won't review them here. And then we use normalization so that we get quantization and we can determine what our constants are. So here are the boundary conditions. Number 1, the wave function must be continuous. Number 2, unless potential energy is infinite, the derivative of the wave function must also be continuous. So you can't have kinks in the wave function. It needs to be smooth so the derivative is not going to jump. If you have an infinite potential, then you integrate the Schrodinger equation across the discontinuity to find how much the slope changes across the discontinuity. Right, so discontinuity in the potential energy function hence. And the final one here, in order for the wave function to be normalizable, it must approach 0 as boundaries approach plus or minus infinity. So we threw away some of our solution parts instantly because we said, well, that doesn't approach 0 plus or minus infinity. Aaron.
So the reason that we didn't integrate the wave function for the infinite square well, because we already had this d sine n pi, the d sine nl equals 0, and we could easily find the quantization.
No, the reason we didn't do it is because it was earlier and I hadn't shown you that step.
Oh, okay.
And so I said, if you have an infinite boundary, there is 0 chance that the particle gets out. It's just not possible. And so the wave function had to be 0. And so we just said, in the case of the infinite boundary, it has to be 0 outside.
Okay.
But then we had, it's continuous for all other cases, which you can find by integrating if you integrate the Schrodinger equation, you have 0 is equal to the difference in the slope on either side of the boundary if it's not a potential function that's infinite. And so that's why it has to be continuous slope. And so later in this chapter, we learned why we have the continuity of slope, which comes from that integrating the Schrodinger equation, and why that was broken on the infinite boundary, because it's the same thing. Okay, so what are the small problems? There are only two small problems. 50 points for the first one, 25 for the second. I've actually broken them down. This is exactly what you're doing, except for you don't know the situations. So your first problem worth 50 points is, and it's actually worth 50% of the test as well, because the problems were 75% and this is 75 points. It's in 4 parts. The first part is you're going to be given a potential energy and it says to sketch it. So you just need to make sure you sketch the potential energy function that's given to you. And then you have find the form of the time independent wave function in each region. So remember, when you have the Schrodinger equation, what's the form of your solution for the Schrodinger equation? Every time it's had the same form, what's that been? Actually, every time, I guess, particle in the box, or the harmonic oscillator wasn't that. But the particle in the box and the infinite wells, what was the form of the solution for the second derivative is equal to a constant? Or actually it wasn't equal to, it was equal to constant times the function, was e to the bx. Whoops, I'm still on the box for some reason. So you do need to know this. Psi is going to have the form of e to the bx for, well, it's going to have that form for yours just like it does for most terms. Right? Because you don't have differential equations, it's not like you're going to solve the differential equation. But you do need to say, oh, psi is going to have that form, and then you're going to find what the b is, or what the b possibilities are in each region. Can you do that?
Do you want us to put the e to the I theta when we're putting the constant in there?
Well, you will have, you need to be correct. So if it has an I, you should have the I. If it doesn't have an I, you shouldn't have it. Oh, wait, you were saying the...
Yeah, the e to the I theta thing you were putting in front of it.
Oh, no. That was because normalization still could be times any complex value with a magnitude of 1. That's what the I theta is. So no, don't do that.
Okay.
That we always just say, take 1. 1 is one of the possibilities here. So you'll need to find what the form of the independent wave function is in each region. So you don't know what the constants are, but you know I have like a e to the ikx plus b e to the minus ikx, or whatever is appropriate for that region. And then you need to apply boundary conditions and normalization by creating equations. You're not solving these equations. So in other words, it's not going to take you a long amount of time to do this. We're not doing the actual hard math. We're just saying, okay, my boundary conditions are, and we have them right here, and so you're going to show that you know what it means to apply those boundary conditions. So you're not going to have to find the quantized energies. You're not going to have to find the constants. You just have to have the equations that you could use to find them had you another 2 hours.
So by normalization, you just mean say, oh, this would go to infinity, I can cross out that solution.
You do need to do that. You do need to take terms that are going to go to infinity. You do need to set to 0. Yeah, but otherwise, like let's take the normalization. You're going to have integral from, let's say you have 2 regions, because that's the smallest number. There's not 1. So integral from minus infinity to a of psi 1 star, and instead of psi 1 star, I'm actually putting whatever it is here, right? That's psi 1 star, and then psi 1 dx plus integral from a to infinity of psi 2 star, psi 2 dx. Come on. Well, imagine that I wrote dx there equals, it stopped reading my pen here. Thank you very much.
If you go off the page, does it just like crash?
I don't know what's going on. You can see it sees the tip of my pen moving around. It won't let it choose. See how I'm clicking on that? I think it's the application died. I'm going to kill the application and try again. This, I believe it's a Microsoft product as well that I'm using. it crashes a lot. It's got reasonably good functionality, except for that crashes a lot aspect. Like every other time I plug this in, it crashes. That wasn't its fault. Yeah. So yeah, it was the app crash. Okay, so and it should have a DX here, but I don't want to risk that again. So you would actually have to write it out with your functions in there, not just saying, and now if I do psi star slide, right?
You write it out, but you don't have to solve.
Right, you don't have to solve. That would be the end of that line. And then write the form of the time-dependent wave function. So what does that mean?
Does that mean doing the full solution? Writing out or multiplying it by the e to the negative?
Yes, that's what it means. That means we're going to have our psi of x comma t is equal to psi, I'll put psi subscript 1 of x. And then instead of putting phi here, you'll put e to the minus. Yeah, I think you're right too. That's what I was stopping to think about. And you can figure that out real quick by integrating that one equation. Okay, so that's 50% of your points in the test there. 25% is going to be in doing 4 commutators. So make sure you review how to do a commutator.
What about that one that you threw out on the homework?
These are not the ones I threw out in the homework.
Sure, but like, would you expect us to do one that was similar to the one that you threw out?
No. These are actual realistic commutators,
Okay.
not bizarre ones. They involve things like X, P, H,
Okay.
the actual operators that we use. Yeah. So those are the small problems we're doing. So you have the knowledge questions, and then you have these problems. So any questions about the test before we shift to looking at problem 4?
For the first small problem, so that's basically going to be one of the problems that we looked at, like if it's
It's not going to be exactly any problem you looked at. It's going to be very similar to problems you've looked at, but it's not going to be exactly any. So it's not a straight regurgitation. It's applying what you've learned to a slightly modified situation.
Do we have to be able to write graphs of what the wave functions look like in each of them?
Not the wave functions, because you're not solving them.
Okay.
You just have to have a graph of what the potential energy function looks like. That's what the graph is. And likewise, you're not going to have the energy levels, so you're not going to be graphing those.
Yeah.
All right.
Oh, I guess I did want to ask.
Go ahead.
What the theory questions would be about. Was that the first couple of slides? Just
Yeah, the theory questions will be covering topics from all the rest of the slides here. All right, going to this one. So let's look at problem 4, because we didn't do problem 4 in class at all, right? I just kind of said, it's there, and we're out of time. So here we have 2 potential energy wells. You might think of this maybe as having, for instance, 2, well, I'm not going to try to make something up. So we have to sketch the potential, and then we have how many bound states does it possess? It's going to take a lot of work to get there.
what is that part?
Well, because that actually is the first place you actually have a stopping point.
Yeah.
So the first thing we're going to do is say, how many regions do I have? So how many regions do I have? 1, 2, 3. Notice it's specified the energy is a negative energy. It's below the level here where I'd say V equals 0 at that line. So we have a bound system because the energy is below V equals 0. If the energy was above V equals 0 here, it would be unbound. I have here, because I have two wells, I kind of expect to find two energy states, one symmetric and one antisymmetric, but I have to do work to confirm that. Remember I said that you have to have an either symmetric or antisymmetric solution for this. That's the only way it works out, which is then going to give you psi mod squared is symmetric in both cases. Because it really has to be, right? You can't say, oh, this side here is side A and it's different than side B. It doesn't work out. So using the same methods as we did with the single delta problem, this here and this here are what we found for the single delta well, the left side and the right side. And then we have the region in the middle, and this one here, I left it in exponential form and I didn't put sine and cosine. Well, actually, I have. Those are exponentials. Those are exponentials because it's once again at 0 here. I don't know what I was thinking. It's not in a box. And so we don't have any i's in this case. And both of these terms aren't going to 0 necessarily because it's not going to plus or minus infinity in region 2. So we could get rid of one of the terms in region 1 and one of the terms in region 3 because it's going to plus or minus infinity. But region 2, it's not. So there's my solution. What do you do after you found that? So this is the solution from putting it into the wave equation, the Schrodinger equation. So what do you do after you put it into the Schrodinger equation? You always apply boundary conditions next. And so my boundary conditions for continuity, psi 1 is equal to psi 2, which gave me that equation at x is equal to minus a. And at x equals plus a, you get this equation. And then we had to do the integral of the Schrodinger equation because it was an infinite boundary, right? We couldn't just say the slopes are continuous because it's an infinite boundary. So doing the integral at each boundary, we have the difference in the first derivatives. And notice this is going from a plus epsilon to, minus a plus epsilon to minus, I still said it backward. Integral from minus a minus epsilon to minus a plus epsilon is what we were doing at the first boundary because the first boundary was at minus a. And so that's why this is the first derivative at x is equal to minus alpha plus epsilon and at x equals minus epsilon. And then this here was what we got from the rest of our work for integrating the Schrodinger equation. And so you can look back at the textbook if you don't remember that. So we now have a condition taking the derivatives. Here's the derivatives calculation. So we have a condition between C, D, and B and kappas. And at the second boundary, we have a similar condition. So just like before, a total of 4 equations. And then I identified I'm going to have either symmetric or anti-symmetric solution. So a symmetric solution would have, and I'm going to come back to these solutions. A symmetric solution would have B is equal to F and C is equal to D. An anti-symmetric solution would have B equals minus F and C equals minus D. Whereas anti-symmetric B is equal to minus F, and C equals minus D. And if you're not sure on that, remember what makes it symmetric? Psi of plus x equals psi of minus x is symmetric. And so if I have x greater than a, psi of plus x would be be to the kappa x. Psi of minus x would be f e to the minus kappa, or yes, f e to the minus kappa, and then since it's minus x, that becomes a plus x again. So the f and b would have to be the same for symmetric. For anti-symmetric, they'd have to be opposite sides. And if x is less than a, then I have c, well, you're just going to flip the exponents when you go from the plus to the minus. So that's where we have our symmetric case and anti-symmetric cases here. And so these equations simplify. You can do the work without identifying the symmetric and anti-symmetric solutions. It's just going to be a lot more work. And as you probably learned by now, unlike what you came to expect in general physics or college physics, in physics, we're often trying to find the most efficient way of doing it, not just, going hard at it. And so we want to identify that symmetry so it's easier. And so applying B equals F and C equals D, these top two equations are the same equation, aren't they? Yeah. And the bottom two should also be the same. Yeah, the bottom two are also the same. So you really only have two equations when you apply B equals F and C equals D. And so here's the top equation, here's the bottom equation. And then we want to try to make some sense out of this. Because I look at those two equations, I'm like, wow, that's tough. And so since this side here is multiplied by B and this side here is multiplied by C, I'm going to divide one equation by the other to get rid of C and B. And so if I call the lower, that's genius. If I call the lower equation 1 and the upper equation 2, then 1 over 2 is going to have the BE to the minus kappa A cancel out on the left side. And so I'm just left with 1 minus 2m alpha over kappa h bar squared on the left side. On the right-hand side, it's a little more complicated. The right-hand side, and I'm going to actually do the right-hand side here just so we're all on top of things. I have C times e to the minus kappa A minus e to the kappa A over C times e to the kappa A plus e to the minus kappa A. So the C's are going to cancel, and this is where we have to go to those hyperbolic. Well, we don't have to, but it makes our life much simpler to go to the hyperbolic functions. So remember I told you sinh is equal to e to the, and I'm going to use kappas here, kappa A minus e to the minus kappa A over 2. And cosh is equal to e to the kappa A plus e to the minus kappa A over 2. So if you look at this, on the bottom we have a plus sign, on the top we have a minus sign. So that means sinh, and that should have been kappa A. Sinh is obviously defined with an argument. Kappa and cosh of kappa A. So sinh of kappa A over cosh of kappa A. I'm not even going to write the 2's because you can see the 2's are going to cancel. So sinh over cosh would be e to the kappa A minus e to the minus kappa A. Very nice. over e to the kappa a plus e to the minus kappa a. Once again, very nice. You cannot write close to the edge here. So what's different between this and what I have in red is that it has the minus is positive, right? The minus is the positive term here. Whereas here I had the minus is the negative term. So all I have to do is multiply by -1. So this here is equal to negative sinh kappa A over cosh kappa A. And just like with sine and cosine, sinh over cosh is tanh. So that's equal to minus tanh of kappa A. I looked down too low. I was like, cos? How could it be cos? It's got to be. And so that's how I got this tanh. And of course, your calculator will do hyperbolic trig functions for you. But what does tanh look like when you graph it? If you graph tanh, which you have to do here, it's transcendental. Just look at look at what I have right here. You have e to the kappa a minus e to the minus kappa a on top, e to the kappa a plus e to the minus kappa a on bottom. For a approaching infinity, then the e to the minus kappa a's are approaching 0. And it's just going to be e to the kappa a over e to the kappa a. So tanh approaches 1 as a approaches infinity. And for a approaching minus infinity, then it's going to be the ones with the minus exponents that are left. And so you have tanh of kappa a approaches minus infinity. Oh, -1. Wow. And so the tanh function is going to look something like that. And once again, you can graph it carefully, but it's a lot shorter to write tanh, and your calculator has tanh built in. And so that's why we do this. It's still transcendental. We have kappa A here, and we have kappa out here. And so we're going to need to make a graphical solution to find where it actually crosses. And note the tanh kappa A has, a function like I just drew. And if I graphed 1 minus 2m alpha over kappa h squared, that's 1 minus a 1 over kappa. Well, 1 over kappa is going to be something that goes. So I'm going to erase this, but here's what 1 over kappa looks like. So we have 1 minus 1 over kappa means that we are going to have, it's flipped so that it's like this. And it's 1 minus that. So it's going to come up. So that it asymptotes to 1. So both of these, both the red and the green, are asymptoting to 1. Yeah. As kappa approaches infinity. And so you plot them and you find where they cross. And when you do that, there's only one solution for each one. So there's 2 solutions. And then we have find the allowed energies for a given alpha. And so then you actually plug in that alpha and get what the solution is. And sketch the wave functions. Hopefully it's on the next page. Well, that's good. I had posted a graph here that somehow didn't come through. Anyway, that's the going through very quickly how to do it. And as you well know, you would never be asked to do all of this on a test because of the time factor. So do you have questions about the process going through that? No?